All right. So in this session, we are going to talk about symbol table construction. So some practical hints on how to do this and how to solve some problems which might not be that obvious, especially problems of the scope of variables. So if you have a variable x declared in a function, and then you also have a variable x declared, for example, inside of a loop body, then the question is how to handle this in your symbol table. So we're building the next step of our compiler. We will enable it to perform semantic analysis. And then finally, the next exercise, so PE6, we will then use lots of the stuff we're building here, especially the addresses of variables. So are they located in some global storage, or are they located locally on a stack frame, or are they maybe strings in a string table? And we will also use this information afterwards to generate code so we can address variables and also functions. So what we need to do is we need to organize identifiers and also strings in order to resolve them to memory locations later on when we really generate machine code. So variable names and function names are text string. So we'll need to have a table of these text strings, and we need to have some sort of index for this. And essentially for building small programs like we do with WSL, we wouldn't really need a hash table, but a more simple solution would suffice. But real compilers very often use hash tables, and that's why we included a hash table implementation in the new skeleton files, PE5 skeleton.zip. And we did this because, well, we're programming in C, and as we mentioned, C is not ideal for some programming tasks, especially when it comes to more complex data structures like trees, graphs, lists, or in this case, hash tables. There is actually a hash table implementation in the standard C library, but it's not really useful. So we built a very simple one, which is also not very efficient, but it works better for our use case. I'm not perfectly sure that this doesn't contain errors. So if you find any errors in this hash table implementation, well, please let us know. All right. So the functions of our hash table implementation are declared in tlhash.h and implemented in tlhash.c. And we have some interfaces to handle the tlhash t. So this underlined t always stands for type declaration. So it's the tlhash type struct. And this interface includes functions to initialize and finalize hash table structures, to insert values, to look up values, to remove values, and also to obtain all the keys in our hash table, and also to obtain all the values in our hash table. Now, since we want to store arbitrary stuff in our hash table, we have not pre-declared any specific data types, so keys and values are just void pointers. And the caller program, so your compiler, needs to manage what they point to. And you can use the symbol t struct, for example, that we also provide to contain this information. So we have a symbol type struct also. So this symbol table struct is located in the ir.h header file. And this consists of, well, a character pointer to a name. So whatever name our current symbol has. So this can be a variable name or function name, for example. Then we have a type of a current symbol, and this is of a type symtype t, and symtype t is simply an enum. And this enum tells us, is this a function, a global, a local variable, or a parameter of a current function? We have a root node of a type function we can point to. We can have a sequence number, which we see later. For functions, we also have a structure element giving us the number of parameters of that function. And finally, we have a pointer back to our local hash table for local names in our symbol t struct. So in general, you should implement 3 tasks in this practical exercise. We've distributed them a bit differently than on these slides on the exercise sheet. So we split them into a bit smaller parts. But in general, the first task is to work with global variables. So our skeleton already initializes a global symbol table called global names here. And in this first task, you should implement the find globals function here. That should fill the global names symbol table with symbol structs for everything that is global. And the things that are actually global in VSL programs are either functions, obviously. So functions have a name, so they need to be in the symbol table so we can find them later on. And all global variables you might want to declare in a VSL program. Functions should be put in their own name table, and whenever you parse a function, you can already fill this with the parameter names because, well, that's convenient because it saves you a second pass. Functions also link to their tree nodes, so we still have our est, obviously, so we need to build a connection from our function table to wherever this function is declared in our syntax tree. And this means when we have a function name, we can look this function name up in our function name table and then follow the pointer to the node in our syntax tree that is the root of, well, this subtree, which actually defines our function here. And to do this, you should number the parameters and you should also number the functions. So giving it unique numbers makes it really much easier to find them later on. Task number 2 now is concerned with local variables. So here we just built this function name table, so we can go through each function separately. And since we built this link to our syntax tree, we can now traverse the subtree for each function separately. And then we can go through this and see declarations and use of names and also of strings if we use strings. So what we're going to do there is we are going to resolve names and strings within this function we're currently looking at. So we're going through all the functions, and for each function we're doing this procedure to resolve names and strings. There's a function bind names, which you should implement here. And the subtree will consist of a mix of entering declared names into a function's local table whenever we find a declaration. And then whenever we find a use of a variable, we need to link the used name to the symbol they represent. And that can be a symbol in our local symbol table or in a different symbol table. For example, if we reference a global variable from inside of a function. We also should enumerate the local variables here, so give each variable a unique number to find them. And then, we can look up the identifiers that are used hierarchically. So if we have a function composed of several scopes, so for example, we have a function, inside of that we have a while loop, and inside of the while loop we have an if. And inside of that if, we have a variable x. Inside of that declared. Inside of the while loop, we have another variable x. Inside of the function, we had yet another variable x. We start at the most inner scope, so essentially at the line which we're currently looking at the current instruction. And then we check, is this variable declared in our local scope, so inside of our if condition. If not, we look it up inside of the enclosing while loop. If not, we'll look it up inside of the enclosing function. And if it's not declared there, then we check if it's a global variable. And if we don't find our variable that is just used also in the global function, in the global variables, well, then we need to print an error just because this variable has never been declared. So what we're doing here is essentially we're doing a bottom-up search of the tree to look up the identifiers, first in the local scope, and then we're going up and up until we reach our global scope in our program. And for our strings, we just create a global index of string literals to be able to find them later on. And finally, the last task is just to destroy this whole structure that you created when it's no longer needed. So you should also implement a function destroy subtree to just clean up the whole thing again. How this works exactly obviously depends on your implementation. So, I can't give you much more tips here without knowing your implementation, obviously. So, global string literal indexes. What are we doing with strings? Now, strings are only used once because we don't have like string variables here, and that happens in the nodes that represent them. So this node presently contains a pointer to the string at the data element. And when we actually want to generate code in the next practical exercise, it would, for example, be great to be able to display all the strings at once so you can get some debugging output here. So for your global string literal index, you take the pointer to a string, you put it in a global, which we call string list here. You keep a count of strings. We call that string C just for string count. And obviously, this is dynamically sized data structure. So if, well, you should, if possible, allocate it dynamically, because static allocations always are very, well, impractical when you really want to use large programs because you're running out of space. So maybe you should just try to resize data structures. So there's convenient calls like realloc that allow to extend, for example, an area you have allocated on the heap. And then, of course, you should replace the nodes data element with the number of the string it used to hold. And then you have a reference from your string table, which has numbered strings 1, 2, 3, 4, 5. And then you can, well, essentially look it up from your node whenever you're generating code later on. So this will mostly become important in the next step, but this is exactly the right step in our compiler construction process to implement this. So let's look at an example here. So this here is the syntax tree you might have gotten. So it's a print statement, and this print statement has 3 strings: foo, bar, and bats. And what you're going to do is you well, iterate through all of your tree, looking for string data, and then you enter this string into your string list here. Then you assign this specific string to a numerical index. You just count up the index for each string you found. And then finally, in your tree, you replace the string that's linked there with just the index. So our code generation step can then look it up afterwards. And as I said, my recommendation, because you don't know how big your strings can get, is to allocate all data dynamically. And you can use these malloc and then realloc functions to just extend or to allocate and extend dynamically allocated space on the heap. Now, local name tables are a bit more problematic. So global name tables are, well, relatively obvious because we're only looking at the top level. So either we find a var declaration for a variable or a def for a function here. Now, if we have local variables here, then we have a problem because, well, like in C, also in WSL, the following code is legal. So we have like a function body here, an outer function block, begin and end. And this declares 3 variables x, y, z, and does something on this. And then we have an inner function block, again, demarked by begin and end. And inside of that inner function block, like in C, we can declare local variables again, which only have a scope demarked by this red dotted line here, instead of the blue dotted line, which is a scope for your complete function. So whenever we're inside of our if here, inside of that block, then whenever we access x and y, we access our local variables here. This code doesn't make much sense, obviously, because they're thrown away afterwards. Don't worry about that. So it's just a stupid example. And whenever we're outside of this if block, we're accessing the local variables x and y, and also z if we use them here. So we have an overlap. So x is a shadow variable for that x here, and y shadows the other y variable in the outer scope. So these are not the same variables. They're stored separately. And nevertheless, in the end, we want something like one single local table of symbols for the whole function. So if we just try to store them using their names, x and y, well, we'd obviously have a conflict as soon as we reach this line of code here. And then we figured out, oh, we're trying to enter a variable called x in our local symbol table, which was already declared in our outer scope. And now this would be problematic. So what can we do about this? Oops. well, this gets a bit confusing with all the pointers and stuff, but I hope it's relatively understandable. So we have a function f here, and this function is just the code we've seen before. So in your syntax tree, it might look like that. We have an outer block here, which is our blue block here. And then we have an inner block, which is the block inside of our if, containing the var declarations here and our two assignments here. So essentially that one here. And when we use a function table here, we could say we have local variables just enumerated 0, 1, 2, 3, 4. And these have names. And as you see, they have unique numbers here on the left-hand side, but they don't need unique names on the right-hand side here. But what needs to be ensured is that we actually link each line of code that either uses or defines a variable, so all assignments and all uses of variables, to the specific enumerated local variables. So this x equals 1 down here in our outer scope, for example, which would be that one here, needs to be linked to local 0 because that would be our outer x. And the same for y equals 2 down here. This would need to be linked to local number 1, to our y, whereas our assignment inside of our if need to be linked to their own variant of local variable, number 3 for the inner x and number 4 for the inner y. And the question is, of course, how can we achieve this? Now, let's see how we can avoid these name clashes for local vars. There's a typo in the headline, I see. So first, when we encounter a function in our syntax tree, we create a new symbol table, which we can call locals here. And this just contains some sort of key, so a hash key for our hash table, and a sort of pointer pointing to the variable here. And when we encounter our outer block here, now marked in orange here, then we create a scope inside of that function here. So our first scope. And well, then we'll continue to fill this first scope. So what we do is whenever we encounter variables in the outer block, we link variables in the outer block scope to our local function symbol table. So essentially what we do is in our first scope that we created, we create links to symbols we allocate here, a symbol X, Y, and Z, which were in the outer scope. And then we link them back. And these on the left-hand side are not names of variables, they're just hash keys, so arbitrary hash keys. And so we can find them using our pointers on the right-hand side here in our local symbol table for our function. So we're still in the outer block. We haven't considered our inner blocks so far. So let's first look what happens when we find the first assignment for x equals 1 in the outer block. So what we have to do here is we need to check which x is actually the one we're assigning to. So we check in our first scope, is there an entry for a variable x? Yes, there is one, and this is linked to our symbol x in our local variable table, and it tells us it's local variable number 0. So what we do is actually we in turn attach this symbol here for the correct variable x we want to allocate something to, and which later on resolves, for example, to a register or memory location when we generate code. And we're linking this back using this purple line to our node in the syntax tree. So again, we're just messing around with our syntax tree, changing it around. And that's why it needs to be so flexible here. And after we did the lookup, we found it here in our local symbol table, obviously, and then we link it back. So whenever we go through our syntax tree again in our next step, we can then generate code from that. And we can do the same, of course, when we encounter y. So we again do a lookup here, find the symbol y, which has been declared before, and then we link the symbol y back here. Now, what are we going to do when we encounter the inner block? And here you see it gets a bit chaotic with all the pointers running around. Sorry for this, but I was running out of space on that slide, I'm afraid. What you're doing is actually you build a stack because these scopes are nested in your program. So you have the outer scope, which is a function, and then you might have the first inner scope, which might be a while loop, and then the second inner scope, which might be an if condition, for example. And you can nest it arbitrarily deep. You can again have a while loop inside of your if, and so on and so forth. So here we have only one level of nesting again. So we have this if condition inside of our function, and this is our second block here. So this has local variables x and y. So what we're doing is we essentially create a stack and push a second scope on that stack. So our first scope still is the scope for our outer function here. And the second scope is the scope for our if condition here. And here we can have separate x and y's, which then link back to new entries in our locals table here for our complete function. And again, what we can do is now we can link them back to our separate symbols here. So they have the same name, x, that's the outer x. This is the inner x, but they have different numbers here. So they are linked to different places in our locals table. And again, if you encounter another block inside of this, so if you go deeper here and would find another block linked here, which is not the case in our example here, you would just create a third scope over here. And the nice thing is, as soon as you exit that scope, so if you arrive back at the block and have worked through all of this, then you can actually kick off this local scope because you don't need that information anymore because you have managed to store all that information in your locals table afterwards. So this is more efficient than keeping all this data around. And so now you can do the same. Look up, for example, if you have this x equals z assignment, you can look it up in the second scope table. If you wouldn't find it here, then you would automatically go up the stack and look it up in your first scope table, for example. Here we find it, so we can add a pointer here, same for y, obviously. And so essentially we can, again, link back the local function entries we've generated when we encountered the var declarations here back to our second scope table. So we know whenever there's an x, it just refers to this entry here in our local table, which has an index of 3, I think. Yes, for example. And well, what happens for our assignment x equals z? So of course, not only the left-hand side, but also the right-hand side variables need to be looked up. So z is not a variable in our local scope, but we find a symbol here, a symbol z, and we can figure out, well, using the links, it's actually in our outer scope here. So we can look it up. We can attach it to that z. So here we now have x attached to a variable that's declared in the inner scope, and z attached to a variable only declared in the outer scope. But of course, since it was not overloaded, still visible in the inner scope. So all variables of the outer scope are always visible in the inner scope, unless the inner scope declares a variable of the identical name. And then, well, when you're finished with that block, you can just throw it away because we have all the information retained here. So essentially you can throw that second scope away when you're finished. So you're not throwing that part of your syntax tree away, obviously. Just when you're finished, you can throw that scope away because you have all the backlinks now to your local variables here in your block. So this is just a temporary data structure you need. And of course, when you finished looking at this function itself, so the outer scope, you can throw away the outer scope variable information because you have all this now stored on your function level. You have all the links available here, and you don't need this additional information anymore for generating code. So that sounds not complicated, and probably it is rather complicated to wrap your head around for the first time when you build this. So essentially, yes, that's why we gave this bit of an introduction to give you a guideline for how to approach this problem. essentially, it's just, again, doing tree walks, symbol lookups, and working with this hash table, but getting this right and all components to work together, admittedly, is a bit of work. Unfortunately, that's what you have to do in a compiler to enable the system to really look up variables and work with different variable scopes and enable you to have identically named variables in an inner scope that have the same name as a variable in an outer scope. We have left out some difficulties like a complex type system because, well, that would take ages to finish, I'm afraid. So we're just happy with our integer variables, I'm afraid. All right. So after we finished processing that function, so processing the subtree, declaring a function, we can clean it up. So all uses of local variables are bound to the respective symbols. It's no longer necessary to look them up by name because now we have pointers to them. And we know keys in our function locals table. That's what remains of our processing of a function here. These keys need to be unique on the left-hand side to avoid collisions with other local variables and params, but not the names because they're replaced here by pointers to specific symbols, which then have their own unique number here. So they're linked up here. So we have the complete information to build a stack frame now, because that's where we store our local variables, obviously. And this means we can just go through our locals table when we generate code for a function, go through all the keys, assign, well, an element on the stack for that key. Since all variables are integer variables, all variables have the same size. That's quite convenient. Otherwise, we'd have to do things with alignments and different sizes and arrays and stuff like that. So here, it's a bit more simple at least. And this is sufficient to build a stack frame and also to generate code that refers to all the variables and symbols here. Because we have attached in the nodes of our syntax tree here all the variables that are used or defined to their respective symbol table entries. So there's no ambiguity if there's an X showing up here. We always know it's this inner symbol X and not the outer symbol X. And when we use it here in the outer function, well, that's difficult to see because I drew over it. It would be the outer X. So what are we going to do if something goes wrong? Like if we are trying to use a variable Q and we only have declared X, Y, and Z. Well, we would figure out when we try to look up that name, well, we can't find it anywhere. So when we look up names, we can now determine if a name is properly declared or not. And then would obviously be useful in that stage of the compiler to add some error message indicating a semantic error, especially while our programs are hopefully semantically correct, but maybe you want to build some semantically incorrect test program, so declaring or forgetting to declare a variable that you use afterwards, for example. And that's pretty helpful, for example, to test if your compiler really catches the errors. So the question is, what should you do if you encounter an incorrect program? Now, well, we didn't specify it. So you can print an error message, you can crash and burn, format your hard disk. So this is undefined behavior. Essentially, an error message would probably be really nice for the user. Yes. Now, real programming languages, as in more complex programming languages, of course, have different data types. So this would also require you to store and verify type information so you don't accidentally assign a floating point variable to an integer variable, at least without type conversions. We don't have that here, so that makes our compiler a bit easier. Extending this is a lot of work, and type systems are a whole area of computer science theory, actually, where many people wrote their PhD thesis on. So this is an interesting topic, but it can be a bit dry at times, to be honest. So I know a colleague of mine, when I worked at Oracle Labs in Cambridge, was working mostly on type systems for new Java versions. And I remember always when he was thinking about something and he couldn't figure it out and he needed someone to talk to, he came over to my office and then we stood at the whiteboard. He drew some type system diagrams and after 15 minutes, I was completely confused, but he was happy just to have someone to talk to. So I guess, yeah, it wasn't that useless. All right. So we have semantic errors. We just throw an error message when we encounter one, and that's perfectly fine. You shouldn't try to fix it. Now, obviously, there's different programming languages. For example, Python is a well-known one, which don't enforce you to declare variables or types. So wherever you'd make an assignment, it automatically determines the type and it can do conversions. So as you can imagine, this requires even more work compared to our explicit variable declarations we use in VSL, and we also use in languages like C or Pascal, which make it easier for the compiler actually to enter this information whenever it encounters a declaration and then use it whenever a variable is used in an assignment or in an expression. What else do we need? Blocks need a name table, so they need it only temporarily. So when we traverse the inner block, when we look up X, of course, we should be able to return that symtab entry number 3 we've just shown just using a simple pointer. And when we're finished with the inner block, we just go back up one block, and then when we're encountering an X in the outer block, we would look up X in the symbol table or name table of the outer block, in this example to resolve to entry number 0. And we've seen we can use a stack of temporary hash values for this. So we push a new one when the block begins. We put in locally declared names and make them point to the real symbol table entry. And then what we do is we look up names recursively in bottom-up order. So we start with our inner scope, as I already mentioned, and then go up until we either find our name in the closest scope, so the first hit we encounter, or we arrive at our globals and still can't find it there, and then it's an error. And then we can just throw away, pop the temporary table off, as we've seen of the stack, of the symbol table stack, when we encounter the end of this block, for example, for our if in our example. So after each node has been linked to its correct symbol table entry, that's what we're doing on the way. We don't need its name anymore, but we still need to number the local variables so we can tell apart variables with the same name on different scopes. So this number is important, for example, to give us an index in our stack frame later on. So we could maybe, if we have numbers 0, 1, 2, 3, 4, we could just use them multiplied by 4 if we just stored 4-byte integers to give us just the relative location of that variable on the stack frame, and essentially also the offset we are going to use from our stack pointer or frame pointer when we generate code later on. We have provided some tree dumps in our current skeleton codes, and we have already provided a bit of code for print symbols and print bindings. And those should display the string table, names and indexes of contexts in the global and local symbol tables, and also the linked symtab entries from the tree nodes in your tree. So we have this PE5 sources and output.zip, and it could happen that your tree dump looks a bit different from the ones we supplied as examples, particularly if you do a bit of different hashing. You might have a different sorting of elements in your hash table. So we didn't sort them by sequence numbers here. So essentially, when you try to check them against the example output, just notice that some of the orders maybe different, but that's not a mistake. That's just an artifact of just looking up hashes in a different order. So some hints for this. So the indexes of functions, parameters, and local variables should match our example output up to the order the things actually appear in. And that makes sense because they actually represent the structure of your input program. So essentially you try to really put them inside of your tables in order. So there's a correct order to count them regardless of how you implement them, because you're just following your tree. And this tree is obviously defined by the structure of your input programs. So these sequence indexes are not arbitrary. So it's not enough that they're unique. Because we'll just use them afterwards, as you see, to calculate addresses in machine level code to figure out, for example, offsets in the global data segment, offsets in our stack frames, and so on. So it would make sense not to invent alternative numbering schemes, because then you'd mess up your whole memory alignment, and that would be difficult to fix. Not impossible, but it would just cause unnecessary work. So those were a number of hints, quite a lot already. I think there's still a lot of things to implement. I hope you can get it to work. If there's problems, as always, reach out to us on Piazza or by email. And yeah, then in the next exercise, we'll finally generate machine code, and we can then try to assemble it and really run our program. We'll have to do a bit of work for this on our side to enable you to do this also on macOS 10. So we're currently restricting ourselves to 64-bit x86 code, as I've mentioned already. So if you happen, like me, to have one of the more recent ARM machines here, then it might be a bit more difficult, especially if you don't have an emulation. We'll try to figure out some things. Luckily, that's over the Easter break, so we'll have some more time to do this also. So that was all from my side. Thanks for listening. I'll stop the recording, stop the sharing first, and then stop the recording.